Hi everyone, it's Nono here, and this is an overview on how we can work with autoencoders with Keras, how we can create them, how we can use TensorFlow to get features or codings from an image or a series of images, and then regenerate those images from the codings, which is also a way to create a network that can generate new images based on the information on a data set. You don't want the network to learn too many features from the images, otherwise it will just overfit and not generalize well. All right, we covered autoencoders at first touch in Live 33, so that's in June 3rd, 2021. You can go watch that live stream. Today we're gonna continue or make a recap on what we did last week. We're going to be following examples from the Hands-on Machine Learning with Scikit-learn and Keras and TensorFlow book from Aurélien Géron. And it's chapter 17. We went through what these things are and what they might be used for, and a bit of the architecture and a bit of the code examples. All right, let's get coding. So we're gonna get here to connect and allocate a new backend. So we have a Python 3 Google Compute Engine backend. We have 12 gigabytes of RAM, 68 gigs of disk. So you can start executing cells. So we're gonna import our dependencies here. And this is just walking through a notebook. This is not hands-on tutorial. We did that last week, so you can go to None of the Math last live 33. This is where we hand coded all this notebook following the hands-on machine learning book, and we're going to continue executing. I don't think when you go through notebook cells that means that you're doing a tutorial, but I'll explain things. So we are here loading the Fashion MNIST dataset. We commented what that is. So that's Fashion MNIST is Zalando's 28 by 28 pixel images with 9 or 10 classes of clothing. So we get the train and validation data from here. We have here the code for a stacked encoder and stacked autoencoder. These are not really stacked. This is just the encoder and the decoder, and then we stack them, I think. And we have a sequential model. We get inputs that are 28 by 28 as we saw on that data set. We have a dense layer of 100. We have another dense layer of 30, and we get those 30 units from here. So the output of this block or this sequential model is our codings. And later, right, so we get the input shapes to be 30, and we have another dense layer of 100, right? So the output of this block goes to this one. We get a dense layer of 28 by 28. So we get back the pixels for our reconstructed image, 784 pixels. And then we reshape that into a 28 by 28 image, right? So we have a stacked decoder there. As I mentioned before, the stacked autoencoder is a sequential model that just stacks both of those Keras networks that we saw above. And after we do that, we can start compiling our model and training. We compile our model. We define this rounded accuracy metric for visualization. It's a custom metric that we provide in here, is defined as a function. And we compile our model with the binary cross entropy loss and the stochastic gradient descent optimizer. Learning rate is 1.5. We can see here that layer 0.output, right, is that 30 units dense layers. So if we go to our network or our model and we access the layers, the layer number 0 is going to be this block, right? So it considers this as a custom layer that we've created, and this would be layer 1. So this is layer 0. So stacked autoencoder layers 0, and then the other one is number 1. Pretty simple, right? And if we output is this here, and input would be this one here. We can actually test that. So I think we can put this here. And all right, so let's keep executing. So we have executed that one. So we define this one, and this one, and then we get our output. In this block, we could actually, as I said, put the input, and we get that like input image size. We could also get the input of the second one, which is 30 digits, and then we can get the output of the second one, which should be that 20 by 28 image. So again, we can leave this here as it was. The shape of the train is like 55,000, 20 by 28. And then the summary, I don't like this that much because, it helps abstracting, but we don't really see the model. So we see that this one takes an input shape of 30, this one output shape of 30 digits, right? And this one of 28 by 28, but we don't see anything in between. Here we train, so this is not going to take a long time. This was counterintuitive to me the first time I saw it. The input and the output are the same thing. And this is what I showed before, that we wanted the image of the landscape, the sun and the trees to be the input, but also get the same image at the other end. And then we also get the same validation data in the input and the output. So after these trains, this would be like maybe 10 or 20 more seconds, we'll have a trained model. Here we have a helper function to show the reconstructed images, and we'll run this to run right after epoch 10 finishes, which is going to be in 3, 2, 1, go. Right, so we're going to go through the model. We're going to get 3 images from the validation dataset, and we're going to try to predict, which means we're going to input the image, and then we'll get the codings, and then we'll get the output out the other end. This is a bit weird because we're inputting an image and we want to reconstruct it, it means that we have the original image and maybe we want to reduce noise because the image might be noisy, it's like a reconstruction, right? And the images don't really need to be there in the training set, right? These images are not in the training set, these are on the validation set, and you can see how they fit and then they get on the other end. So the ones on the top are the inputs and the ones on the bottom are the outputs. And what was interesting to me that I didn't get to do yet is that we could get codings, so just the digits on the middle, and change them, randomly generate 30 digits and then input them in the network and then see what we generate. What we're doing here is that I'm printing the output of the autoencoder, right? I'm predicting here with the autoencoder only, so predict XY valid, and it's giving me 30 digits. And then we're plotting stacked autoencoder predict. We're predicting with a given image, and then I'm printing the weights of the layers. So this wasn't really anything important because the weights are the same in both, because that's the weights on the layer after training. So on that specific layer after training. And here we can see that we get the summary of the autoencoder, but we also get the name of a layer and the output of a layer. We can see it here. And in here we define a feature extractor. That means that we define a new model that has the inputs of the stacked autoencoder inputs, and then the outputs of the stacked autoencoder output of the first layer. What I did is that I defined the entire network again. So I define it again with the encoder and the decoder here. So on the summary, we can see the full network, not just 2 sequential layers. We train really quickly. We're not going to train for the entire time. And then we define a feature extractor. So we're going to get the inputs and then the outputs. And the inputs are the original input. So it's a 28 by 28 pixel image. And the output is from layer index 2, its output, right? That is actually the output of this network. So we're actually, with the train network, we're getting now a new subnetwork that if we give it an input, it's going to give us the result of this layer, not the image at the end, but the result of this layer here, right? So we go here, we actually get, for the 2 first images, we get the codings. So these are those 30 number digits that I was mentioning before. And if we get the summary, we can see that we have that input layer and we have that output layer. If we were to get the second stacked autoencoder that we have here, so let me add a code cell here and I print a summary of the entire network, you see this part here, right? So here we have 81,000 parameters. Here we have 163, like double 1,000. And the part that I couldn't get to is that I wanted a subnetwork that will get an input in here and then put an output in here. To make this network work in here, I had to remove the part here that defines the input shape. And I'm not sure, maybe I can do that now. I'm not sure if I'll be able to, but I don't think I can specify that, right? Input shape 30, is that it? It works, but I'm not sure if we're going to be able to do it. So we're training, get the summary. Okay, now this one here. Okay, Model inputs must come from Keras input, thus holding pass layer metadata. They cannot be the output of a prior known input layer. Here, a tensor specified as input to model 3 was not an input tensor, it was generated by layer 30 unit dense. So we're going to have to re-execute some of the cells, manage sessions, so we're going to terminate the other one. I'm just going to execute these two because we're going to go straight. We don't need this definition here. So we define this here, so we're going to train this, and we have our feature extractor. All right, so what we want to do is we have a decoder model. So I'm going to try with the same settings we have. This works, but now we don't want the X-train here. We want the codings. So if I go here and put here X-train, let's do shape. So we have 5, so 28 by 28 images. But if we predict with that, so if we do feature extractor encoder, so we'll do codings would be X-train. So let's see codings shape. Let's just try that. Okay, so we get 30 digits, 55,030 digits, right? So that's what we're obtaining here. And maybe we can try to visualize a few of those. So these are digits, and so let's say we get just one, right? We get just one of those codings. And this is a 1D array plot image. Can I plot this image? So Keras display image. Okay, let me see. Rank 3. All right, this is what this is like the hack. Rank 3. Keras black and white to color image. All right, so here I'm getting into a sort of a rabbit hole. Grayscale to RGB. All right, this is what I'm looking. Just helper methods. Maybe we just were missing this thing. Okay, show. Okay, so let's see if this works as well. All right, so the image is there. It's really small, but it's there. Maybe we can do this plot image now. Plot, where is plot image? Plot image. This is really simple. I don't think we should just use that method, but let's try it. Okay, all right, this works. All right, so with this, what I'm doing is I have 3 digits, which is 0, 2, 5, 5, and 125, and I'm visualizing them as color, right? 0 goes to white. This is weird because it's inverting the colors. So print image, let's see. All right, so we have a way to render that. So let's now render those digits. So if I have here a TF expand dims and I get this axis 0, so we put that there, right? Expand dims and then axis 0. All right, so this way I can do MPA array now, and we get there. Now with this function here, we can get any array. So we can say digits. So we get these digits and we put them here. We make an array of them. So let's say we put here all of these ones, and we go here. So we go from digits to like a tensor, and then from that tensor or array, this is actually also like an array, to an image, right? So here we have a gradient from white to black, and this is because this should be the other way around actually. So image invert. Okay, so that's there. Pill is not defined. Image ops. Cool. All right, so now I'm happy because we get here, let's say with 0s and 1s, if we were to do 0s and 1, we'll get black, white, black, white, black. So that's what we get here. If we use 255, so we can make like a gradient or something. So this like black, white, gray, black, white. And if we want to do a gradient, of course, we just do a gradient, right? So here we get a gradient. All right, so why am I doing this? This is because in here we've gone from a series of digits to a plotted image, and we're going to make a helper function. So we're going to do here a plot. So def plot digits, and we'll input a set of digits, and then we'll maybe just digits to image, and we'll just do this. We'll just put this thing here, and we'll just return. Let's do it here. And I never know if I should just return here or if it's better to know what this variable is and then return it. So here we have these digits. So we do, our image would be digits to image, and then we have the digits, and then we just plot the image. And we should see the same. We could make another that is like plot digits, and then we just do plot image digits to image digits. And here we should just do plot digits, and that's it. Okay. Can we run this multiple times? Not great. What we're gonna do now that we have the helper method there, we had some codings. So we have some codings here. So if we get now a cell and say, okay, codings, what is codings 1, right? We have this. Can we 0, right? Yeah. So can we do this? So can we plot these digits? Yeah. Okay. So these codings belong to an image, right? So we can say, okay, I have, so codings would be, for instance, okay, so an image, right? So we can say an image is xtrain, and we get the first one, right? So we say plot image, right? So that's our boot, right? And for this same image, we can say image codings would be, and we now get our feature extractor encoder. We get our image in, this is the actual image, but we want as a batch. So we're getting image as batch, and then we get here image, let's just do here image as batch, and then we get the actual image. So we can input here this image as batch, and we print the image codings, and let's see what they are. So we run this one and this one. So we have a TF tensor, and again, so we need to do the number 0. So we print the numbers, and then we do the image codings 0. So this image is encoded right now by our network like this. It's not going to work perfectly because we have trained only for 2 epochs. It's taking us some time to get here. And you can test now that if we do this, right? So if we get now a shirt, now the codings, so I'm going to save this just so you trust me on this one. So let's see if I can just put it here. I do that, and then the codings are different. So this is our shirt, this is our boot. And that's right now, I don't know what it means, but these are 2 different representations or 2 codings that belong to different images. And if we were to fit them into the decoder, I will get from here, we go to here, and then from there, we go to that image that we saw before, right? So from here, we'll go to here. So here, then to the codings, then to this image. And I'm trying to understand how we can train a decoder model. So we have this here, we'll get 30 digits as inputs. We will combine the decoder model, and then we will feed it. So we have now our codings, which are those that we had before. So we know that for our codings, so we're going to call them xtrain codings. That might be more appealing. Oops. All right. So we have that. We run these things, and now note how I'm inputting those codings and then I'm outputting xtrain. So let's see what happened here. But receive input with shape, input 0 of layer, blah, blah, none. Input 0 of layer 1. Let's see. So what is the input? So that's, okay, flatten. Okay, let me see if I can do here. TF Keras layers, input shape 30. Let's see if this works. Is right dimension. Flatten. Shape. Okay, so it's shape, not shape. Okay, so shape. I think what I'm doing is exactly the same that this was doing. So maybe that just means that it doesn't work. So I could do directly there. Okay, this is not it. So here, so it would be something like this. But yeah, I don't think this is gonna work. To have value 30, push it to have value 30, 20, 28. Okay, so fit xtrain codings, x valid. No, let's try this. So shape 30, we get 100 activation cell. Decoder model summary. So decoder model fit validation. So it's a bit weird. So what is the layer? So the sequential 5. Okay, sequential layer. Expected access manual 1 of input shape to have value 30, but received input with shape none. Okay, so here train coding, but xtrain shape is 20 by 28. X none, that's Y. Oh, okay, validation data. Okay, so validation data. Okay, so how did I miss that? I don't know. So we do here x valid codings equal feature extractor encoder x valid, and then x valid coding. Okay, so this is print and this is print. Great. So that seems like now we might be onto something. So x valid codings. So hopefully that now runs. Oh, it doesn't. Okay. History, decoder, model, fit, X-train, footings, X-train, epochs, 2. Let's comment this out. Okay. All right. So this works now. So it seems like the validation data is the one that is failing. At least let's see, decoder, model, predict. If we give it X valid codings and we get 1, we get something that seems like an image. So image, reconstructed image. So we reconstructed image 0, maybe. Awesome. Okay, great. So we need to figure out how to add validation data without error. X valid. Great, but this is really cool. So this means now that if we got the codings here, which is like plot, so plot digits, so maybe just get that. So these are the digits, and for those digits, we're getting this image, right? Awesome. Let's add categories here. Reconstruct an image, right? So from digits. And now we're going to generate a synthetic image from random digits. Let's see what happens here. So digits to image, right? Digits to image. Yeah, but now we need the actual. So if we print this, the shape of this, so shape, that's 130, right? So we actually have a tensor, so we can do a TF random uniform 30. I don't know, like 130. I don't know if that's how you do it. All right, so let's take a look at this, the shape of these inputs. So we had some inputs here. It's actually a tensor with the same shape, I think. So 130, and then here we're generating 130. That's awesome. So we can generate a random image. So these are our digits or codings, random digits, and now we reconstruct the image, right? So we plot digits, random digits 0. So we have that there. Trying to expand them with 0. Let's see. Okay. So let's try plot digits. Oh, okay. So I see. So let's do this. Okay, now this works. So these are random digits, and then that's an image. This is pretty cool. So we're generating random images. We could make a GIF, something representative of this. So I'm wondering how I could do this. So if I could just save manually, which is going to be a bit annoying. So this would be coding 01. Probably this is something that we would need to automate. All right, so we'll leave it at 3, but in those small images, you can see like the activated parts that are more common probably for the random activations. So let's go to the desktop and maybe make a bash script. It's going to be a GIF, so montage and then a GIF. All right, so that would be 01, 02, 03. And for each of them, we're going to do something like dash, tile, 1 by 0. Geometry is going to be 256 by 256, and we're going to have here codings 01 PNG and then synthetic 01 PNG. So that'll be it. And then this is 0 and this is 3. Not sure how this would look, but let's just try it. With image magic, that is what I'm using here. You gotta be really careful, because if you don't put an image, an output image, right, name, then you will overwrite the original image that you provide last. In this case, was the synthetic. So now we have that. So now we have these images, which is a montage, and make these ones 56 by 56. All right, we got it. So we got these things, and each of these ones is a coding. Now this is a bit weird because I actually prefer removing some information from the codings, but leave the other images as they are. So you see, these are the actually hard to see. So each of these images contains the codings at the top and then the image that we generated for each of them. With this, we could make a GIF. So we could make a GIF here. Okay, and this is our animation. So this is what we've done. For each of the encodings at the top, you get an output at the bottom. And I don't know, they're not great, but that is in some way what we get. This way you can, we could even generate a random digits. We could, let's say, generate a synthetic image from cherry-picked digits. And that way we could tweak what we have. So instead of doing random digits, we have a uniform we could do a series of digits. So df convert to tensor, and we could have here like now a list of numbers. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's do actually just zeros and 1. Well, so we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll do 10, 10, and 10. And maybe we'll just make these ones 1. All right, digits, tensor. All right, so that's our tensor. So we see the shape, it's 130. And now we can reconstruct the model. So we can plot digits, and then we get the digits tensor, right? And then we reconstruct our image with the digits tensor. So that's our image. And let's actually, how can I do this? It would be good that these things auto-save. So we're going to make a weird way of making an animation, but I think it's going to work. So we have this image here, and let's just make slight modifications to this, and you're going to see what the encodings mean. We're recording also, so that's making an animation automatically. And also, I don't know how much this is going to be changing. We'll see, because we need to see also the threshold of values in the original images. Okay, so this already works. Let's keep going. Maybe we can be a bit more radical here, changing faster, and you're kind of guessing what I'm doing. All right, so we're transitioning between different input codings. Okay, that was a bit fast. I don't know how that happened. Let me just take one more step. This would make sense to be automated, but what I wanted to show you now is that these two are the same. I didn't regenerate. Okay, this is what I just wanted to do, and I think if we make it a GIF, this is a GIF, and if we go really small, this is interpolating between different types of shirts and dresses, right? Like you can see that change in activation on the map. And yeah, so if you zoom in, you don't see anything. We're just like merging and looking at different things. But what we've managed to do is to activate different parts of the encoder, of the decoder, when we go from codings and random codings that we're just like writing by hand into an output. And one thing, we're going to continue with this because I'm really enjoying. So what's happening here is, or what's not happening is that we haven't trained for more than 2 epochs, either the encoder or the decoder. So the codings that we're using are not well generated, and the decoder doesn't work either. So we're gonna have to train for longer epochs to see the results. We'll see that next week. So I'll close up today's live stream with this, right? So this is, I don't know where it is, like there, with this GIF, or maybe there, this GIF that I'm happy that we've got here. So we've explained what stacked autoencoders are. We've seen what it means to encode an image into digits and then decode it. We've discussed why you might want to use this thing. We've written or like gone through the code that we wrote last week with a stacked autoencoder, with an encoder and a decoder. We've used the feature extractor to create the codings and get those codings from the entire data set. And we've created a subnet with the decoder where we can input a coding of an image and then reconstruct that image. So generate synthetic images from new codings that don't come from existing images. Go ahead and like this video if you want to support the channel, and subscribe if you want to get notified when I go live next or when I upload new videos. You can also join the community at None of the Massless Discord. And yeah, thanks so much for watching, and I'll see you next time.